Okay. Does this factor? Did anyone get it? No? Okay, well, this is going to be an issue. What's a little confusing about these instructions are the way it says, then use your calculator to find the length correct to 4 decimal places, right? So they want they want you to they want you at this point, where is it? Right here. Right here. They want you to plug it into like Wolfram Alpha, okay? What I'm trying to get you to is to see a way to try and do it algebraically, right? Because like the one I did with sine, like number 3, right? Number 3 in this problem set is sine x. And remember in class I tried sine x and we couldn't do it. So you could do that in Wolfram Alpha, which we did in class, right? Remember? Didn't someone, right? And so you can do it. It's just by hand it's harder. That's why they say just use the calculator. But this is a hint as to how to get to that. It's re-looking at that numerator like this and seeing if you can factor it down. The ones from 7 on are ones that you can do by hand. You don't need the calculator for. So, I mean, I don't want to use, we've already used 20 minutes. I don't want to use more time. Yeah. No, it's just like the one I did in class where I showed you couldn't do it by hand, but you can do it with Wolfram Alpha. It says use the calculator. That's what they mean. Yeah. So you'll get some decimal answer from Wolfram Alpha. Yeah. Okay, anything after 5? No? Yes. Same section? Natural log cosine x? All right. This one's more like it. This one's more like what you'd see on a test. Y equals natural log cosine x on the interval 0 to pi over 3. Right? So the first thing that you'll do is, draw a graph perhaps, if you want to do a graph. But since this is a function of x, we have the formula for it, don't we? We're okay to just use the formula? So we'll go integral from 0 to pi over 3. We want the arc length. So 1 plus the derivative of that. What's the derivative of natural log of cosine x? I'll do that on the side here. What's the derivative? What's the derivative of natural log of anything? 1 over it times derivative of what's inside, negative sine. So isn't that just negative tangent? And what do you get when you take negative tangent and you square it? Tangent squared, right? So this becomes tangent squared x. Garvik, does that make sense? Or did I go too quick? Is that all right? Okay. And then at this point, we have to figure out this integral. But what is 1 plus tangent squared x? Secant squared x. So that's the square root of secant squared, which is just secant x. And then the antiderivative of secant x is one of your formulas. So natural log, blah, blah, blah. Plug in pi over 3, plug in 0. Subtract. Have I gotten to a point where you're okay, or you want me to keep going? That's okay? Done? That okay with everyone else? Dot, dot, dot. Any others? That was pretty clean. I mean, there's not a whole lot to it. No, not that one. Okay, I'm going to move on to today's material. We're going to go 7.5 to start. And this is going to be areas of surfaces of revolution. So we've already taken curves and we've spun them around the x and y axes to get volumes, right? A volume. And then we did arc length. That's where we took the function off the page and we straightened it out and we measured how long it is. Now we want the surface area of a function revolved around an axis. So this is going to look very similar to what we've already done. Take some function, take it between 2 points, wrap it around the x-axis. But instead of looking for a volume, we want the surface area of the outside of that object. Different measurements, right? Surface area and volume are two different things. So the way we do it is like we did last time. Remember I had taken a little piece in here like this. See a little red piece there? Take that little red piece and blow that up over here. All right, remember that? And we did that little piece, and then we constructed a little right triangle here, didn't we? And we said the length of the hypotenuse is approximately the length of that arc. Add them up, that gives you the length of the arc length, right? Instead, we're going to take that piece, right? That piece, and we're going to take that little hypotenuse and imagine wrapping the hypotenuse around the x-axis. What would you get if you took that little hypotenuse there, up there on the graph, right in this region, and take it and wrap it around the x-axis? You would get something that looks like this. Wouldn't you? Approximately something like this. Oh, yeah. Right? And it's hollow, right? So it's just like a piece of tape or something going around. It doesn't have volume to it. And if I take that and I want to know its area, so I want to know what it takes to paint the outside of it, then what I could do is come in with my scissors again. I could cut it, right? Cut it down the middle and open it up and lay it out. And it would be like a strip of paper, wouldn't it? And that strip of paper would look like this. How high would this be? What would be the thickness of the paper? Be careful because everyone's always ready to go dx right away. But think about what the length of this is. Isn't that this piece right here? Isn't that little piece right there? Isn't that the hypotenuse? The hypotenuse is approximately that length, isn't it? The square root of 1 plus f prime squared. So that little piece right there is the little infinitesimal arc length, isn't it? Do y'all see what I'm saying or not? Yes. Okay. Then how long is it? Now this is connected to our shells method. Remember the shells? If I want to know how the distance from that little arc up there down to my x-axis, isn't that just the function itself? Isn't that the function? So the function is the radius of this circle, right? This circle right here has a radius of the function, and when I cut it and lay it out, it's the circumference of that, isn't it? What's the formula for circumference? 2 pi times the radius, but the radius for us is the function, f of x. And then over here is the square root of 1 plus f prime x squared. So that would give you the area of that one piece, which is just one of the infinitesimal slices of our function. We want to add them all up, right? So our formula would be, what do you think? Integral from a to b, 2 pi f of x times the square root of 1 plus f prime x squared dx. That formula should look extremely familiar to us, right? There's only one thing different between that and arc length, right? The arc length formula had that square root. All this is arc length, isn't it? All we've added to it is the 2 pi f of x. That's all we've added. So that is the formula that will give you the surface area of the function revolved about the x-axis. Now I put a little thing together here. I didn't put it together, but I've been using Mathematica, which isn't very useful to you because a lot of you don't have Mathematica. So there's a free program out there called WinPlot. And there's a lot of free graphing utilities out there, but this one, I've been using it for years. If you get WinPlot on your computer, go to do a 2-dimensional graph. I'm gonna just pick a function out of the blue here that I want to wrap around the x-axis. I'm going to take square root 1 minus x squared. Right there. So it's like a little half circle, okay? Semicircle. That's actually half of the unit circle right there. And imagine between -1 and 1 taking this thing and wrapping it around the x-axis and looking for the surface area. Wouldn't that be the surface area of the unit sphere? Right? So what you can do with this is you can go to this, you can click on 1, which means one-dimensional calculations. Go to revolve surface around the x-axis. See the arc. Oh, you know what? I'm actually only going to be revolving just for now this from 0 to 1. Okay, I can go from -1 to 1, but just for now I'm going to go from 0 to 1. When I revolve that around, click see surface. I'm going to throw in the XY axes here, XYZ axes. Can you all see this thing revolved around there? Oh, that didn't come out too good. Let me take out the shading. No, that didn't help. That still didn't work. Yeah, maybe change it. It looks great on my computer, but doesn't look too great over there. Let me just go with something lighter. Yeah, that works great. Yeah, I don't know why. Let me take fast draw off. Yeah. All right. Like I said, it looks great on mine. Let me try one more thing. Try this again. Okay, I'll just leave it like this, gridded out like that. You can kind of see it's hollow inside that way. But do you see that's the half circle rotated around the x-axis, right? So we're just trying to find the surface area of that. All right, so let's do that as our first example. All right. Well, I'm going to give you a more general question. I'm not even going to give you a unit circle. I'm just going to give you a general circle. Okay. All right. Here we go. This will be a cool example. Find formula for surface area of a circle of radius little r. Now, any of us could flip to the book, could flip to where we have our geometric shapes right here in the back of the book. Go to sphere. Area is 4 pi r squared. Okay? But we need to show that it's 4 pi r squared. All right? Using calculus. So the first thing I'm going to do is just make sure we understand surface area. That's not a circle radius r. That's a sphere. Yeah. Surface area of the sphere. Change that circle to sphere. So a sphere of radius r is really the same as taking half of a circle like this, right? And revolving it around the x-axis and asking for the surface area. Do you agree with that? So this has radius over here, little r, radius over here, what? Negative r, right? Little r. We good there? I need to know the equation of that thing. So I'm going to start by writing down what's the equation of any circle centered at the origin, radius r. X squared plus y squared equals r squared. That's the equation of any circle centered at the origin, radius little r, right? Can you solve that for x or y? I mean, in this case, we want to solve for y, so it's a function of x, right? Y equals square root of r squared minus x squared. So that's what you would get if you solve for y. Now, technically, when we take square root, we'd have plus or minus, wouldn't we? But we're only going to look at the plus, which gives us the top half of the circle, because that's all we need in order to revolve, don't we? Okay, so let's set up, well, let's not set up the integral. What are the things we're going to need for the integral? Because we're using that formula we just had. Integral from a to b, 2 pi f of x. Do we have f of x? Yes, that's it right there. Square root 1 plus the derivative of f, so we'll need derivative of that squared. So let's take the derivative, which is, what's derivative of square root of something? 1 over 2 times that something, root of that something. So 1 over 2 times the root of that something times, though, chain rule, the derivative of what's inside. Careful, r is a constant, right? R is a constant. The only variable here is the x. So what's the derivative of r squared minus x squared? Negative 2x. Which I can write as, let's cancel the 2's, negative x over square root of r squared minus x squared. Are there any questions on that? Sure? We're good? Okay, that's y prime. What am I supposed to do with that? Square it. So let me square it. I'll do that right here. Y prime. Notice I'm using y prime instead of f prime of x. You can use either one, whichever one you want, all right? So square it. Squaring it's nice. The numerator turns out to be x squared. Denominator, the root goes away, right? R squared minus x squared. Bam. I'm liking it. So all of that is ready to go into my formula for the surface area. The formula for surface area is integral from a to b. What's a and b for us? Negative r to r. 2 pi times the function. What was the function? Square root of r squared minus x squared times the square root of 1 plus x squared over r squared minus x squared dx. Which looks horrendous, doesn't it? It's not that bad though. Okay, it's really not that bad. Y'all ready to go after this? All right, inside the square root, common denominator. So what are you missing on the bottom here? R squared minus x, so you put an r squared minus x on top. So you'll have, I think just to save some time, I'm going to just take this piece right here, everything in this root, I'm just going to work on it right over here real quick. I have square root of my common denominator gives me an r squared minus x squared plus x squared all over my common denominator. Is everyone comfortable with how I did that? Yeah? R squared minus x on top and bottom here, combine the two, you get this. The x squareds cancel. And you're left with square root r squared over r squared minus x squared. And that's equal to r over the square root of r squared minus x squared. I can take the square root of top and bottom, can't I? Okay. That replaces that whole thing. So I'm ready to rewrite this integral. The integral becomes integral from negative r to r of 2 pi times square root of r squared minus x squared times r over, holy crap, is that right? Square root of r squared minus x squared dx. Nice, real nice, right? Because the square root stuff just goes away completely.
Is that why you didn't take out the square root on the previous step?
Is that why I didn't take it?
Top and bottom. You left it.
Why I did what?
You just canceled out the r squareds, but you didn't cancel on the one on bottom.
Down here?
Yeah.
Well, I can't do anything to that. I can't turn that into r minus x, right? Because it's separated by subtraction. You can't do square root of each one, right? So I couldn't simplify that.
I guess that makes sense. It's circumference.
What's that? What's left? 2 pi r dx. And so everything in there is a constant, isn't it? What's the antiderivative of 2 pi r with respect to x? 2 pi rx integrated from here to here, right? Because 2 pi r, these are all just numbers, like 5. The antiderivative of 5 with respect to x is 5x, right? So 2 pi r, antiderivative is 2 pi rx. Now plug in r, what do you get? 2 pi r squared minus, now plug in negative r, what do you get? Negative 2 pi r squared. Add them together. The negative and negative become plus. You get 4 pi r squared, which is the formula for the surface area of a sphere. Hey, and just FYI, I didn't do this in class. I just never came around to it. If you want to know the formula for the volume of a sphere, the volume of a sphere radius r, then you're wrapping that same function around the x-axis, aren't you? But you're doing washers, the first method we ever learned for volumes. So do you remember what the formula was for that? Integral a to b pi function squared dx. So if you would have taken integral from negative r to r of pi times, what's our function here? Square root of r squared minus x squared, and you square that, dx, this would give you the volume of that sphere. Do you understand where I got that formula from? Okay. I'm going to do this because it's so damn quick. Negative r to r, when you square that, all you get is r squared minus x squared, right? dx. And then I'll even split this into two integrals. Negative r to r of pi r squared dx minus integral negative r to r of x squared dx, pi x squared. So all I did was split this into two integrals. What's the antiderivative of pi r squared with respect to x? Pi r squared x, evaluated from negative r to r, minus whatever I get here. What's the antiderivative of pi x squared with respect to x? 1/3 pi x cubed from negative r to r. Y'all follow what I did there? Let's plug in and see what we get. What happens on this integral, or this, when we plug in r? We get pi r cubed minus, now plug in negative r, you get negative pi r cubed. With me? Minus, there's my minus sign. Now let me do this in brackets here. First plug in r, what do you get? Negative 1/3 pi r cubed. Or no, not negative. I'm putting the minus here. So 1/3 pi r cubed. And then minus, what do you get when you plug in negative r? Negative 1/3 pi r cubed. Let's put all this together. What do these two together become? 2 pi r cubed. Okay, what does this in here become? That's minus minus plus. 2/3 pi r cubed. So minus 2/3 pi r cubed. So what's 2 minus 2/3? 4/3. 4/3 pi r cubed, which is the formula for the volume of a sphere. If you look in the back, right? 4/3 pi r cubed. So all of your common geometric shapes can be found this way. One of the easier ones to do, I'm not going to show it, is the volume of a cone. That's 1/3 pi r squared h. All you have to do this is to do what? How do you get the volume of that cone? Anyone? Take a line, segment, like this, and wrap it around the x-axis. And that's a cone. And you can come up with formulas for the volume and for the surface area. Make sense? Yeah. So those are some, things you could do with those. So I've given you a formula for surfaces of revolution, right? I'm not going to do any more. You get the basic idea, right? You have a function, 2 pi times the function, square root, 1 plus the derivative of the function squared, go to town, right? So for the homework, out of that section 7.5, homework is going to be 5, 7, 9, and 11. As you might imagine, you can extend this and you can wrap things around the y-axis. Every problem I'm going to ask you on the homework is just around the x-axis. But if you go y-axis, then you change it to be 2 pi g of y square root 1 plus g prime y squared. So everything changes dy instead of dx. All right. Well, I've eaten up so much damn time, it's crazy. In addition to this, what I'd like for you to do, where is this? I want you to read 7.6, page 404 through 408. I'm not going to cover this in this class, but I am going to give you at least one problem on your next test for this. It's applications of everything we've done to physics and engineering. So I'm going to have you look at the section in 7.6 on moments and center of mass. So you basically have some sort of object and you want to try and find its center of mass. You use integration to do that. I want to see how you can read through this and kind of figure it out on your own. And then I will at some point do a problem in class, but I want you to read through it first, okay? I might walk into class next time and have a quiz that says, give me the formula for the center of mass. And it's not April Fool's. This whole semester has been an April Fool's joke, right? Yeah, y'all are kidding, right? All right, chapter 8, series 8.1, sequences. So we're a little more than halfway through the semester, right? Feels like a lot more than halfway. And we are now going to start chapter 8, which is for me the big chapter. And we're just going to see how far we can get in this, all right? So we're going to start out by talking about what are called sequences. So I don't want you to erase everything we've done in your mind, but just realize that a lot of what we have done is somewhat disconnected from this idea, all right? So, you know, all this integration by parts, all that sort of thing will play a role, but it won't be a huge role. So if you kind of struggle with some of the other ideas, this might be good for you, all right? So sequences. What I'm going to do is first start out by defining a sequence. A sequence is a function from double struct, that's a double struct capital N, to double struct R. All it is a function. Now look, we've dealt with functions our whole life, haven't we? A function like x squared, sine x, you know, weird ones, natural log, you know, functions have been there the whole time. And basically what we've done is we've been able to plug anything we want into these functions, haven't we? Like anything that works. If I define f of x to be x squared, then it's perfectly fine for me to plug in 2, right, and get 4. So that function takes the number 2, spits out 4, doesn't it? But I'm not restricted to just numbers like 2, 4, 6. I can plug anything I want into that, right? I could plug in 1/3, and it would spit out 1/9, right? So it goes from 1/3, spits out 1/9. But I don't even have to go with fractions. I can go with irrational numbers. I could plug in pi if I wanted to, and it would spit out pi squared, right? So the functions that we've always dealt with in our entire lives have not gone from script n to r. And I haven't even told you what script n is yet. They have gone from r to r, meaning you give me a real number, I spit out a real number, right? Real number in, real number out. The script n, the double struct n there, means that instead of being allowed to plug in anything we want, we are only allowed to plug in the natural numbers. The natural numbers are the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now what we've done is we've restricted our domain. All right? So a sequence is just simply a domain restriction. So as an example, instead of using f of x to tell you that, you know, this is a function, I need to somehow tell you this is not a function, a sequence. So you need to restrict the domain. And to do that, I write a sub n equals n squared. Now, by writing it a sub n, or a of n, not a sub n, a of n instead of f of x, this tells you you're talking about a sequence as opposed to a function. But they do the same thing. They square what you put in, right? This one does. So I can say a of 1. What's a of 1? 1. What's a of 2? 4. What's a of 3? 9, right? The thing is, I'm not allowed to plug in anything else other than those counting numbers. That's it. So if I tried to go a of pi, it would be like, "Brr, nope, not allowed. Okay? Syntax error, yeah.
Does it only go to 10?
No, it goes forever. Okay? Any natural number forever. So the script n, double struct n, is the set of numbers 1, 2, 3, forever and ever, amen. Okay? Dot, dot, dot means keeps going. So if you were asked to graph a sequence, like an XY, it would not be a continuous function, would it? Wouldn't be this nice smooth thing you could draw. It would only be picking out points on that function, wouldn't it? So if I compared these two, like if I took a graph and I had, let's say, in blue is x squared, right? That's f of x equals x squared. Then a of n equals n squared would just be what? 1, 1, 2, 4, right? 3, 9. It would just be picking points off instead. That's a sequence. Function going from the natural numbers into the real numbers. Now what comes out? The output, right? The 1, 4, 9 does not have to be a natural number. I'll give you another example of a sequence and you'll see what I mean. Any questions up to this point?
Then you put negatives.
Yes. Well, you can't plug in -1, -2. No, you can't. Natural numbers 1, 2, 3, and on. That's it. If you do negative numbers, then that's going to include, that's the integers. So now you're including positive and negative. So here's an example. A sub n, or I keep saying a sub n, you'll see why in a second. N over n plus 1. Okay, this is a sequence. What happens when I plug in 1? Come out to 1/2, right? That's okay. See, the number that comes out, it can be a real number. It doesn't have to be an integer. It can be a fraction, decimal, irrational, doesn't matter. Okay? A of 2 would be 2/3, right? A of 3 would be 3/4, and so on and so forth. And this sequence keeps going forever. All right? Now there are such things as finite sequences where we stop at some point, like let's just go let's go 1 through 100, and that's it. Those are called finite sequences. Everything we study in this book is infinite sequences. They just keep going forever. All right? Still following me? Now a little bit about notation. I'm going to put this next to this. Because it's somewhat a pain in the butt to write a of 1, a of 2, a of 3. Instead of that, I write a sub 1, a sub 2, a sub 3, and it means the same thing. It means take your function here and replace your n's with 1, 2, 3, and you get the same exact results, right? 1/2, 2/3, 3/4. But that means I can also write the actual sequence function in this notation also. Instead of a of n, I write a sub n, and then I write n over n plus 1. And that would give me the 1/2, 2/3, 3/4, blah, blah, blah. So that's just a different notation, all right, for the same thing. No questions? All right. Next example. List the first 6 terms of a sub n equals -1 to the n times n exclamation point. So you have to first know what the exclamation point in mathematics means. What does n exclamation point mean? Anyone know? Anyone know what we call that? What is it? Anyone ever seen it? Factorial. So I'm going to do this in red because this is a little side note, okay? N factorial means n times n minus 1 times n minus 2 all the way down until you get to 1. So as an example of that, 5 factorial means 5 times 4 times 3 times 2 times 1. Which is something. I'm not going to compute it, but that's what it means, okay? So what would the first 6 terms of this sequence be? Let's get back to the question. A sub 1 would be negative 1 to the 1 times 1 factorial. What's negative 1 to the 1? Negative 1 times 1 factorial. What's 1 factorial? 1. So this just turns out to be negative 1. What's a sub 2? Negative 1 squared times 2 factorial. What's negative 1 squared? Positive 1, and then times 2. What's a sub 3? Negative 1 cubed times 3 factorial. What's negative 1 cubed? Negative 1 times 3 factorial is 3 times 2 times 1. So 6, so negative 6. Do y'all see how this is happening? You see what's happening here? Now this sequence is what we call an alternating sequence. Why do you think we call it alternating? It's switching signs. It's going negative, then positive, then negative, then the next one will be positive. What part of the sequence, the function, the formula, is making it alternate? The negative 1 to the n, right? That negative 1 to the n is what's creating the alternating sign. Do y'all see that? Very important. Negative 1 to the n. Every time we go out one more, it switches the sign, positive and negative. What's alternating sequence? Okay, I could go through the rest, but I'm not going to. All right, you get the idea of what you're supposed to do, right? Okay, how about this? Find a sub n for this list of numbers. So you see how in this example we got out negative 1, then 2, then negative 6? Negative 1, then 2, then negative 6. That's a sequence of numbers, isn't it? Negative 1, then 2, then negative 6. Then we have another number, right? And they keep going. That's a sequence of numbers. That sequence of numbers came from this function. So what I'd like to do is I'd like to give you the list of answers, and I want you to come back and generate the sequence that created it. Okay, so how about this? 1. Well, you know what? Let me do this. 1. Oh. Well, we're going to go real basic first. Negative 1 to the n? Was that going to work? Negative 1 to the n, if you start, you have to start at 1. So the first guy has to be positive 1. You don't want it to be negative 1. You could put a negative on the outside of it. I agree. You could also do something else. No, because negative n power would drop into the denominator. N plus 1. Good. N plus 1. See, all that does is when you plug in 1, it actually creates a 2. And when you plug in 2, it creates a 3. So it switches when it's even and when it's odd. Do y'all see that? Now you said before, though, you said, why can't I? Yeah, I just put a negative 1 in front of that, right? Yes? That's what you were saying? Well, what's the power on negative 1? Positive 1? Aren't these the same bases? Negative 1 to the 1, negative 1 to the n? What do you do when you have the same base and you multiply? What do you do to the exponents? You add them. What's n plus 1? N plus 1. So you actually, this is this,
Awesome.
just put together.
Awesome. Yeah. Two ways.
Question, is that unique? Is that the only way we could have done it?
Probably not.
What if I would have done n plus 3?
Doesn't matter as long as the number's odd.
As long as I start off, when I plug 1 in, as long as I start off with an even, I'm good, right? If I plug in 1, I get negative 1 to the 4th, don't I? Which is positive 1. The next time, I get 5th power, which would give me negative 1. So there's actually an infinite number of ways I could represent that sequence. But there's wrong ways to do it too. But those two ways are correct. How about this way? Would this one have worked? How about n minus 1?
No, because you get 0.
Okay, what's negative 1 to the 0?
1.
1, right?
Yeah, but
And then when you plug in 2, you get 2 minus 1, which is 1, which is negative 1 to the 1, which is negative. And then when you plug in 3,
okay.
you get 2. So it's going to work too. Also, it's going to work also, right? Do you see that? Okay, let me give you another one to try. Oh, don't worry. It's all good. We're all going somewhere with this, all right? Okay, see if you can figure out, find a sub n on this. So here's the sequence. 3 over 2 minus 5 over 4 plus 7 over 8 negative 9 over 16 ... Forever and ever, amen. I'll give you a second to try and figure this out. My advice to you is this. This is the way I always look at sequences. First, look at the signs. Is it alternating? If it's alternating, take care of that first. Get the alternating out of the way. If it's a fraction, focus on numerator and denominator separately. Is there a pattern in the numerator? Is there a pattern in the denominator? Talk about it amongst yourselves. Let's see if any of y'all can come up with this a sub n. All right, I think that's about enough time. Anybody have it? Anyone think they've got it? No? No? Okay, tell me about the numerator. Any pattern in the numerator? Yes. Not x. Can't use x. Uh-huh. Okay, you want to go for it? Okay, that'll take care of your odd, your positive negative thing, right? Okay. 1 plus 2 to the power of n? Like this? 2 to the power of n. Let's see. 1 plus... Yeah. It's damn close. Just one thing in the numerator is all you have to fix. What's wrong? So I know someone here has, the numerator needs to be something other than 1 plus 2 to the power of n. 1 plus 2n. Just 2 times n. Okay, but let me get to that. Very good. Let me get to that. Let's act like that didn't happen, okay? Let me go back here and say this. So what I notice when I see this is I've got positive, then negative, positive, then negative. You can always make things alternate by using -1 raised to an n or an n plus 1. If you want it to start negative, then you use what? -1 to the n, like up here in this example right here, right? -1 to the n starts you negative, and then it should go positive, negative, positive, negative. If you want it to go and start positive, then you use this one, -1 to the n plus 1, or this one, or this one. I just use the -1 to the n plus 1. That's what I always use, okay? So I know right off the bat that I'm going to need a -1 to the n plus 1 to take care of the alternating part, okay? The next thing I notice is that if I forget the signs now, because I've already taken care of that, all my numerators are odd numbers, aren't they? Odd numbers are connected to even numbers. Aren't even numbers all like, 2 times 1, 2 times 2, 2 times 3, 2 times 4? Odds are just the evens plus 1, right? So if I start with 2, 3 is 1 more than that. 5 is 1 more than 4. How could I create even numbers? 2 times n, right? 2 times n would create evens. But I want odds starting with 3, so plus 1. So what happens if I plug 1 into this right here? I get 2 plus 1 is 3. What if I plug in 2? 4 plus 1 is 5, right? Plug in 3. 6 plus 1 is 7. See? That'll create my odds starting at 3. So I've got the signs taken care of. I've got the odds starting at 3 and going. Now I need to notice a pattern in the denominators. It's just 2 to the first power, 2 squared, 2 cubed, 2 to the fourth. So isn't that just 2 to the n? Right? 2 to the n. Raised to the n. That's my a sub n. Now there's always more than one representation for sequences. I mean, there are a lot of times there's more than one way to write it. So that's why when you gave me that, I was like looking at it just to see if there was like some sort of algebraic simplification that would turn ours into looking the same. But so you might get something a little different than this, but it should still create the sequence. So do we need to check it or not? I mean, I can check the first one. What's a sub 1? -1 to the 1 plus 1, 2 times 1 plus 1, all over 2 to the 1. So I'm going to get -1 squared, that's positive 1. 2 times 1, 2 plus 1 is 3, over 2 to the first power, it's 3 halves. That's the first one. Then you could check the next one, the next one, next one, next one. Okay? I'm going to do one more. -4 over, oh wait, hold on. Yeah, I don't want to do that. Sorry. My apologies. -4 8. Negative 8, hold on. Positive, this one's going to be a little challenging, so give me a second for this. Mm, 4. Sorry. Just give me a second. Let me write it down first, and then I'll tell you what it is. So negative 4. Negative 4, 0. Now, I didn't reduce these fractions on purpose to try and help it be a little bit easier to get. Yeah, I think so. Okay. I'm going to help you through this one, all right? What about the signs? Is it alternating? No. So you're not going to be playing with the negative 1 to n power or anything like that. Okay, let's look at the numerators. Well, we only have fractions for part of the time, the rest of the time we don't, right? But every number can be looked at as a fraction, can it? So any pattern in the numerator. They look like evens, don't they? I mean, like if you just look like right here, this looks like evens starting what, negative 2, then 0, 2, 4, 6, 8. So it looks like possibly evens there. And what about the denominator? See anything there? 4, 8, 16, 32. You recognize those? They're all powers of 2, aren't they? They're all powers of 2. So maybe I can rewrite this. I still don't know about this negative 8. I've got negative 2 on top. I've got, my next one's got a 0 on top. Next one a 2 on top, and then a 2 squared. And then a 4 on top, and then a 2 cubed. And then a 6 on top, and then a 2 to the 4th. And then an 8 on top, and a 2 to the 5th, right? Do y'all see that? Does the bottom follow that pattern? Let's see. Where's the problem part? I mean, what am I still like kind of confused on here? Kind of everything over. Whoa, oh, gee. Kind of everything over here, right? All these things right here. I just don't quite have the formula form, or what's there. But if I follow my denominator across the bottom, what would it have to be? If it followed this pattern, 2 to the 1, and then 2 to the 0, and then 2 to the negative 1, right? That's what would have to be on the bottom? Well, 1 is what you plug in. But what you get out, these are the things that come out. So doesn't my denominator follow that pattern, right? What about my numerator? It's following the pattern, right? 6 down to 8, then down to 4, then down to 2, then down to 0, then down to negative 2. And then what should the next numerator be if I follow the pattern? This should be a negative 4, right? But what is 2 to the negative 1? That's 1/2, right? What if I flip that 2 back up? What does it become? -8. You see what I'm saying? This 2 to the -1 is really a 1/2. If this up here was a -4, -4 over a half is -8. So if I extend this pattern across, make that -2, -4, and make the bottom follow this pattern, then I've got it. But that took some squeezing to get out, right? So let me write out the sequence again now. It should be -4 over 2 to the -1, -2 over 2 to the 0, 0 over 2 to the 1, 2 over 2 squared, 4 over 2 cubed, 6 over 2 to the 4th, 8 over 2 to the 5th, and so on and so forth forever and ever. So what would the general thing be here? Now this is, again, we got to go through this to kind of get used to it. I need evens on the top, right? How do I create even numbers? 2n, right? 2n? But if I do that, what's the first even number I'm going to get? Because I have to start with 1, right? Then I plug in, if I try 2n on top, here, I'm trying to write my sequence here. If I try 2n on top and I plug in 1, I start with 2. I want to start where? A -4. So how do I go from 2 to -4? I take 6 away. Now when I plug in 1, what do I get? 2, take away 6, that gives me 4, -4. Then plug in 2 for n. 2 times 2 is 4, take away 6, -2. Now plug in 3, what do you get? 0, right? And then it keeps on going, then 2, 4, 6, 8. Y'all see how that creates that? Now over. Yeah, now you need to start out, you know, it can't be 2 to the n because that'll give you 1, right? 2 to the 1, that doesn't, you need -1. So you need to subtract from that 2, right? So that way if I start out at n equals 1, I get 1 minus 2 is -1. When I plug in 2, 2 minus 2 is 0. 2 to the 0, what's 2 to the 0? 1, so that's okay. I'm not dividing by 0 or anything, right? And then the rest of it carries on. What do y'all think of this? It's kind of weird, right?
That's silly. I mean, like, I don't know what you want to use it for.
Yeah.
Just patterns, games.
There's a bit of kind of weird intuition on these where you just gotta, it's kind of like integrals a little bit because you gotta kind of see it happening before it happens. And
It's kind of fun. It's kind of fun.
all right, we're gonna start a new note here now. Limits
Oh no.
of sequences.
The fun of games, you throw the limit in there.
All right. A sequence, I keep doing that. A sequence, A sub n, has a limit called capital L if the limit as n goes to infinity of A sub n equals L. Now look, remember functions had limits? And we said take the limit as x goes to infinity? And what that meant was what's our function doing as we go out to the right? All this means is where is our sequence headed? Where's the sequence going? Is it heading towards a certain number or not? Right? Okay, if this limit exists, we say the sequence, or A sub n, converges. And we've already seen that sometimes limits don't exist. If not, A sub n diverges. So our sequences are either going to converge or diverge, right? Converge or diverge. Now, let me do an example first. Let's look at one that we've already had. Does a sub n equals n over n plus 1 converge? Well, let's write out the first few terms. Okay, let's see what's happening. What's this sequence written out? I'm not going to write a sub 1, a sub 2, a sub 3. I'm just going to list the sequence as a list of numbers. What do I get when I plug in 1? 1/2. Next one? 2/3. Then 3/4. 4/5. 5/6. Is that headed somewhere? Like, is it getting closer and closer to something? 1. But the way we're going to do it is the way we did every limit in calculus, and that's we're going to take the limit as n goes to infinity of n over n plus 1. But what's wrong? I mean, like, if we did this in Cal 1, first of all, we used x's, right? And when we did this in calculus, even if it was an x, we'd get infinity over infinity, right? So we would have to use what? L'Hopital's rule, right? But L'Hopital's rule requires that your function be continuous. And these aren't even functions because they're just a bunch of dots sitting out in space, right? So right now we can't really work with this until we use a theorem. And the theorem is what I'm going to give you next, okay? So I'm put question mark here. Here's the way we'll write this. Theorem. I think I'll do my own note, or a new page. Theorem. This theorem is pretty intuitive. It makes sense once you see it. If a sub n converges to L on domain R, in other words, if the limit as x goes to infinity of a sub x equals L, then the limit as n goes to infinity of a sub n must equal L. What the hell am I saying? What am I saying? That's confusing as hell. I'll put a little thing on the side here. X element of R here, n element of the natural numbers. So what I'm trying to get at is this. If you look at your sequence as a function, in other words, if you're allowed to plug in real numbers instead of being fixed on the integers, then it's a function like Cal 1, isn't it? If that Cal 1 function goes somewhere, then your sequence has to go the same place, right? Because the sequence is just bits and pieces of it, isn't it? So I'm going to give you a visual example of this below this. As an example, let's say I take the function f of x equals 1 over x versus, in blue, a sub n equals 1 over n. Now, this one I'm allowed to plug in anything, right? Well, except 0. This one I'm only allowed to plug in 1, 2, 3, 4, 5, 6, forever, right? But if I graph them together, then the black function is a solid curve that does this, right? And as I head out to infinity, right, the function drops to 0, doesn't it? And the a sub n is just picking up points along that function, right? So it's got to go to the same place also. That seems pretty intuitive, right? If your function's headed there, then so does. So that means that wherever L'Hopital's rule tells us it goes is where the sequence goes to. So I'm going to go back to that example now. So when we're trying to find, does a sub n equal n over n plus 1 converge, technically what we need to do is try and find the limit as n goes to infinity of n over n plus 1. But I can't do L'Hopital's rule because that's not continuous. So what I do is I switch it to limit x goes to infinity, x over x plus 1, where x is a real number. So you could probably get away with it by just doing L'Hopital's rule on top and bottom here, but technically you're looking at it in a different light. You're saying, look, let me look at it as a function of x where x can be real numbers. Now let me apply L'Hopital's rule, and then the other one's got to go to the same place. So L'Hopital on that gives you what? Limit x goes to infinity of derivative of top over derivative of bottom, but that's just 1. So we're done. That means that this limit up here must equal 1. What's that? You have a question? L'Hopital's rule. I did L'Hopital because remember this goes to infinity over infinity. So anytime you have infinity over infinity or 0 over 0, you can apply L'Hopital's rule, which you take derivative of the top and bottom separately, and then whatever that limit is the same as that one. All right, let me do another one. Converge or diverge for this one. Find limit n goes to infinity of sine n over n squared. Where does this go? Well, do you get infinity over infinity? As n goes to infinity, what's sine of infinity? What's sine function doing as you go out to infinity? It's oscillating. So is that going to 0? No. Is it going to infinity? No. Now the denominator is going to infinity, right? But I cannot apply L'Hopital's rule to this because I don't have the form 0 over 0 or infinity over infinity. In fact, we'd say the numerator doesn't exist. That limit does not exist, right? Well, yeah, hang tight. Hang tight. Well, no, because even if you, like, what's sine of 1? 1 is 1 radian. Then 2 radians, then 3, then 4, then 5. That's still going to give you something funky. In fact, I put together a quick little demo for you. It is bounded over infinity. Yes, it is. Very good. Where is it? I put together this thing this morning to kind of illustrate what's happening here. This is a sequence. This is a sequence plotter that I coded up real quick. Hello. Come on. Work. Work. There it goes. Okay, let me make this a little bigger so everyone can see this. Okay, so what I have here is basically my x-axis is really like my n-axis, and this is like my my y-axis. So input output. Right now I have only plotted 1 point. Do y'all see it? It's really hard to see, but that's it right there. If I plug in 1 into this, I get some value. So that's sine of 1 over 1 squared. Yes? If I start adding more points, they start skipping around here. I need to change my y-min. Let me just throw a whole bunch of these in here. Kind of, you know, it's kind of growing too slowly there. Let me just change it to make it a little easier to see. There we go. Can you all kind of see that it looks like a sine? Like here's one point, then it comes down, then here, then down, down, up, 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 down, down, up, up. Like so, it's kind of like a sine. It's oscillating, but it looks like the further you go out, it's approaching, it's getting narrow. So it's still hopping on top and bottom of 0, but every time you go out a little more, it's getting closer and closer. So, you know, you start throwing a bunch in there like that, and eventually it starts to look like the sine curve, or a sine curve. But you get the idea there, right? Kind of. So we need to somehow come up with that on our own, right? While I've got this open, the previous one was n over n plus 1, right? That's what we did the previous one. This is n over n plus 1. See that? That's that sequence. So it was what, 1/2, 2/3, 3/4, and it's marching. Every single one of those is getting closer and closer and closer to 1. Will you ever get there? No. You'll never get there, right? Keep going forever. You'll never get to 1. So, but we have a limit. It's approaching something. So for this one, what we'll have to use is the fact that the numerator is bounded, all right? The numerator is bounded, divided by something that goes to infinity. Now, bounded means what? That this numerator function is stuck between two numbers. And we know every sine function is between -1 and 1. So if you got something that's bounded, the biggest it can be is 1, the smallest it can be is -1, and the bottom is getting huge, that's going to smash it down eventually. I mean, no matter what, it's stuck. Now, technically, the way to do it is what's called the Squeeze Theorem. I'll show you how you would start it. You start out by sine n. Here's how you would start. You'd write the inequality that you know is true for sine, right? Does everyone agree with this? Sine is between -1 and 1, right? Then what I do is I divide every term by n squared. N squared, n squared, n squared. Now that looks like my problem, doesn't it? In the middle? That's the one I'm trying to figure out where it's headed. So what I can do is look at what the outside ones are headed to. What happens to this left side as you go to infinity? As you let n go to infinity, let n go to infinity on both of those. What happens? You get 0 here and 0 here. So the left and right hand sides go to 0, which forces your middle one to also go between those two, which is 0. The only number between 0 and 0 is 0. Right? So that's the Squeeze Theorem. But what I would accept is bounded over infinity. Oh, wow. Is it already time? Dang. All right. Well, let me see if there's anything that you can do out of this section. Yeah, I don't think you can. Yeah, you can. Good. All right. So you have the homework for the surfaces of revolution. You have the reading assignment for 4.7. No, 5.7. Whatever. And then out of this one, this is from 8.1. This is page 434, numbers 5 through 8. So what they do here is they give you a sequence, the list of numbers, and they ask you to generate a sub n, just like I did in class, right? Those ones that so see how you do on those. And we will pick up with that and get into series next time. Stay on top of your work. Don't fall behind.